Welcome back to this video on ATC. In this video we are going to start with minimization of automata. Then we are going to cover a few more topics, which are pumping lemma, the equivalence as well before pumping lemma, then context tree grammars, then leftmost, rightmost derivations and parse trees, ambiguity in grammar. Then we are going to cover finally the pushdown automata, the language of PDA. Now let's start with the minimization. The automata that we are going to use for minimization is on the screen. So this automata is simply designed to accept strings that contain only one, for example, and any number of zeros. For example, 0 0 0 0 1 would be accepted, or 0 1 0 0 will be accepted, or simply 1 will be accepted. So but as you can see here, this automata is highly exaggerated, so we can obviously minimize this automata. I have already converted this automata into a transition table so that it will be easy to implement the table filling algorithm. Let's start with table filling algorithm here. So in table filling algorithm, we construct table like this. Let's start with B, C, D, E, F, and here let's start with A, B, C, D, E. So as you can see here, I have not added A in x-axis and not added F in y-axis, as you can see here. Or sorry, yeah, the reverse. So why have I not done that is, if suppose we have A over here, then why would we need this cell at all? Because we already know A is simply the same. This A and this A is simply the same, so we will not require A here. Similarly, we will not require F here as well. So this is how you construct the table. Now we have to mark the cells with cross mark to indicate that the corresponding states are not same. So the first rule that we will follow in table filling algorithm is that we'll see which are the final states. So which are the final states over here is E is a final state, D is a final state, and C is a final state, and A is an initial state. So now let us start the first step. We have C as a final state. So the final state and non-final state, those can never be same. So we'll cross those cells over here. So C and A. C is a final state, A is not a final state. So we can cross this. CB as well, and here CF. So F is not a final state, but C is a final state. E is also final state, and D is also final state, and C is also final state. So these two states remain uncrossed. So next final state we'll take is D. Here D is a final state, but A is not a final state, B is not a final state. Here as well D is a final state, but F is not a final state. Right. Again the same for E. E is a final state, but A is not a final state, B is not a final state, and F is not a final state. So the first step in table filling algorithm is done. The next step is to check every cell the behavior of the corresponding states, so that we can tell that if both the states are same or not. So let's take this cell first. So the corresponding states are A and B. Let's see A and B here in the transition table and see their behavior. We have when we give 0 as input, we have B and A. So if we see this cell in the table filling algorithms table, the cell AB is not marked yet. Now let us see the another behavior of A and B, that is when it is given 1 as input, it is C and D. Let's see C and D cell here. Is it marked? Not yet, right? So we cannot confirm that A and B are different states. Let it be. Now let us take CD, right? CD. So this cell is what I am talking about. So C and D, right? And their behavior is EEFF. We can directly say that it is not different, right? So we'll mark we'll not have to mark this. Next is EC, this cell. So EC, let's take EC here. So EEFF, here again we can directly say that these are same. We cannot conclude that these are same right now, but we can say these might not be different. So let's go to next cell, that's ED, E and D, right? Again here also we can see the behavior EEFF. So these are not different as well. Now let us see the cell AF. So A and F, right? So BF, are BF different? B and F not yet marked, not crossed it. So let's see another behavior, that is C and F. Are C and F different? We have that cell here, right beside here. So C and F is marked already, so we can mark this cell, that is A and F are different. Now F and B, right? Let's take F and B. We have AF. So is AF marked as different? Yes, we just marked it different, right? So these are different. Now let us once recheck the cells that we have left it unmarked. So AB, we have AB, C and D. Is it marked? CD? No, right? C and D is not marked. And other cells as well, CD, EF, right? And CE, it is again EF, and ED also is EF. So we have segregated the states that are same and that are different. So now let us group the similar states and mark it as consider it as a single state. So AB, is one state, and we can see that C, D and E all are same states because these three cells are not marked, and the remaining one is F. So now let us reconstruct the automata. We have AB as initial state. We are marking AB as initial state because it contains A, which is the initial state of the previous automata, the automata we initially took, right? Then we'll need this transition diagram. So let me copy this. Let me take this. So I'll take this. Okay. So when A gets 0, it goes to B, right? So this is a self loop because B as well is in the same state. So this is a self loop, and then when A gets 1, it goes to C. So C is inside the state C, D, E that we created, and also C, D, E are final states, right? So since it contains final state, this was also a final state. So when A gets 1, it goes to C. So it comes here, right? And when B gets 0, it goes to A. So it's again a self loop, and when B gets 1, it goes to D. So again, when this state gets 1, it goes to the final state. So this is clear. Now when C gets 0, it goes to E. So E is inside this state itself, so it's a self loop again when it gets a 0, and when it gets 1, it goes to the state F. So again, let's see the behavior of D, which goes to E when it gets 0 and F when it gets 1. So the behavior is same as C. So we have to not mark anything else in the diagram now. Again for E also it is same, E and F. And for F, when F gets 0 or 1, it stays in F. So it's a self loop again, 0 and 1 both. So as you can see here, clearly see in this automata compared to the initial automata, it clearly conveys that it accepts this string that contain only 1 1 and any number of zeros. So this is minimization. Now let us prove the equivalence of these two automata. Instead of taking a new problem, let us take these two automata itself. We have transition diagram, transition table of the initial automata over here. Let's have the transition diagram of this automata, the new automata that we have created. Let us mark these states with a new name. Let the state with AB be Q0, this state be Q1, and this state be Q2. So the transition diagram for this would be So I have created a transition diagram for this this automata as well here. Now let us combine these two transition tables and create a table filling algorithm table. So again, as we saw in the previous problem, we have to leave one state in both the axis. So here let us leave A, B, C, D, E, F and Q0, Q1, Q2. Here we shall start with A, B, C, D, E, F, Q0, Q1. Right. Let me sketch this table. Right. Yes, here Q0 is the initial state and Q1 is final state. So let's begin with the first step of the table filling algorithm. We have C as final state, so A is in the final state, B is also not a final state, Q2 is not a final state, Q1 is a final state, but Q0 is not a final state. Right. Then right, F is not a final state, E is a final state and D is a final state. Now D, again A is not a final state, B is not a final state. In here with this column of D, 2 is not a final state, Q1 is a final state but Q0 is not a final state, F is not a final state but E is a final state. Let us repeat the same for all the final states. So E, A, B, Q2, leave Q1, Q0 and F. Again for F is not a final state, sorry. So Q1 is a final state, A is not a final state, B not final state, and C is a final state, D is final state and E is also final state, but F is not a final state. Q0 is also not a final state. Right. We have completed the step 1 of table filling algorithm here. So let's again do the step 2. So AB, let's start from one side. So AB, again AB, like we saw previously, it is not different. Let's check the behavior once again. Anyway, so AB, so when it gets 0 it's BA, which is not marked at. CD is also not marked because both are final states. As you can see in this table, this cell is not marked at. So again let's come to this cell which is CD. Let's see the behavior of CD, E and FF. So it's not different. Let's see E and EC, right? EC. So EC, again EF. So it's not different. Let's go to ED. So E and D. So it's not again different. FA, BF is not marked at, but CF is marked. So CF is marked over here. So let's mark this. Again we have FB, which is BF here. So AF we just marked it, right? So let's mark this as well. as different. Now Q0 and A. So Q0 and A, we have A and Q0 here, right? So we have A and Q0 here. When it gets 0, it gives B and Q0. Let's see B and Q0, which is not marked. So again, when it gets 1, it is C and Q1. Is C and Q1 marked? Not yet, right? So we cannot say this is Q0 and A are different states. Now let's go to Q0 and B. So B here and Q0. We have the behaviors over here, which is when it gets 0, A and Q0. A and Q0 is not marked yet. D and Q1. D and Q1 as well is not marked. D and Q1 is not marked. Right. Now let's go to Q0 and F. So Q0 and F and Q0, right? When it gets 0, F and Q0, which is not marked, right? Again, F and Q1. Is F and Q1 marked? Yes, it's marked. So these two are different. Q0 and F are different. This is how we mark when we combine the tables of two different automatas and try to see if both the automatas are equivalent or not. So let's go to next cell, Q1 and C. Q1 and C. So EQ1, EQ1, E and yes, here E and Q1. This is not marked, so we cannot mark that. F and Q2, FQ2, it's not marked. And now Q1 and D, D and Q1, EQ1 is not marked. FQ2 as well is not marked. FQ2 is not marked, right? Then Q1 and E and Q1. So E and Q1 again when it gets 0, so E and Q1 is not marked. F and Q2, F and Q2 is not marked, so we cannot mark that as well. So now Q2 and A and Q2, B. So when it gets 0, it goes to B and Q2. So let's see, B and Q2 is not marked yet, but C and Q2, is C and Q2 marked? Yes, it is marked. So we will, yes. So Q2 and B and Q2. So A, Q2, we just marked it, right? So we can mark this as well. F and Q2, F and Q2, F and Q2 again, F and Q2. Oh, so we cannot mark this. Let's go to Q2 and Q0, Q2 and Q0, Q0 and Q2 again. Cannot say Q1 and Q2. Let's see, Q1 and Q2. Oh, why is it not marked? I did miss one. So Q1, right? Q1 is a final state, but Q2 isn't. So we have to mark Q1 and Q2 over here. We just missed that cell in the step 1. So now Q0 and Q2 is the cell which we were discussing now. So Q0 and Q2. So when it gets 1, it gives Q1 and Q2. So Q1 and Q2 are different. So we shall mark this as well. So now we can check all the cells again and confirm it. So we can see that there is no other cell we can mark as different, so this is fine. Now let us see which states are similar, right? So A and B are obviously similar because of this cell, and Q naught, A and Q naught are also similar, so Q naught is also similar, right? And this is one group, and we have C and D as similar because of this cell, and we have CD. Yeah, because of this cell we can confirm that CD are same, and E, so CE, so it is also same, and again here C and Q1 is also same, so it joins the same group. And F and Q2, this is the only cell which we have not seen it, we have seen everything else, so F and Q2 are similar. So we can see here that every node in one automata has a corresponding node in the another automata, and also the initial states over here. The initial state of the initial automata is A, and initial state of the derived automata is Q naught, so both are in the same group. So thus we can say that both the automatas are equivalent. The next topic we are going to address is pumping lemma. So let's take a language, so 0 to the power n, 1 to the power n, where n is greater than 1, right? So let's take an example of this example string of this language, which can be 0 0 1 1, or let's have one more 0, right? So now so what pumping lemma states is that we must consider this word as combination of x, y and z in this form, and the length of x and y should be greater than or equal to a certain number, and y should be at least one character length, so it should be greater than or equal to 1. So here we can consider xy as 0 0 0 and z as 1 1 1, and here y should be at least 1, so let's have it as let us take y as 0 and x as 0 0. We can take anything else, but it's your wish. So here what are we trying to prove with using pumping lemma? We are trying to prove that this language is either regular or non-regular, right? So regular is when we can create a DFA out of this language, that is with the states and the delta, right? We represent states with capital Q and a transition function, a start state and final state, and the initial state we usually use q0 and a final state, and also the set of alphabets, right, sigma. So if we can represent a language in this in the form of DFA or NFA, it can be called a regular language, but as you can see here, we can find no way to represent this language in the form of DFA. But is that a fact that we cannot convert represent this language into a DFA enough to prove that it's not a regular language? We'll need a derivation, right? So the pumping lemma gives that procedure to prove any language as regular or not regular. So this is how we should do the first step, and then we should take a random value k. For this instance, let us take as 2, and if x, y repeated k times and z belongs to the language, if this condition is satisfied, this is a regular language. If it has any one instance that does not follow this language, follow this condition, it is not a regular language. As you can see here, x and y repeated k times and z. Is this how this language is 4 times 0 and 3 times 1? The language is to have n number of zeros and n number of 1, that is equal number of zeros and equal number of ones. But here we have 4 and 3, which is not equal, so this does not belong to the language. So this language is not regular. Let us take another problem on pumping lemma. So we have language WWR, that is the reverse of W, where W is a string of zeros and ones, right? So here let us take L is equal to 0 1 1 0, and again let us take the reverse of this 0 1 1 and 0. This is simply the same string, right? This is a palindrome, but let us take a different one. Let us add a 1 over here. So we have this string. Now let us divide this into xyz. So let xyz be 1 0 1 1 0 and z be 0 1 1 0 1. It is just our wish how we can take this, divide this string as we wish, and x is equal to 1 0 1 and let y be 1 0, right? So and let k be 3 this time. So x y k, y to the power k, and z is equal to 1 0 1 and 1 0 3 times and 0 1 1 0 1. So is the first half the reverse of second half? This is the first half and this is the second half. So we can clearly see that it is not the same, right? It is not the reverse, sorry, it is not the reverse of the second half, or the second half is not the reverse of first half, right? So this is not a valid string in this language. So this language as well is not regular. Right. So this was the small concept of pumping lemma. Now we shall see the context free grammar. Context free grammar. So this concept aids us to capture the patterns that cannot be captured with automata, the DFA or NFA. That is, we cannot with the languages that cannot be captured with a regular expression, and finally the languages that are not regular. So we can capture those patterns using context free grammar. So what is a context free grammar? So we represent a context free grammar as the set of variables and the starting variable and the alphabets in the variable, or the set of alphabets in the variable, that is used in the language, the set of alphabets, and finally the rules of the grammar. So let's directly jump into a question. Let us take the example of expressions in our programming language. So let us consider these expression. Let us take the subset of the expressions that we use in our programming languages. So we have to pass these strings and check if these strings are valid. So we can have brackets, we can have identifiers. So we can have A and B as identifier, particularly for this case, and we can have a star as well, like this, and we can have anything else. So let us consider the expressions like this, right? So we'll have the variables that we are going to use in this set, and obviously the alphabets that are used in this language are A and B, and we also have the star, plus, and the brackets. So these are the set of alphabets, and then finally we obviously have a start string, right? The start string will represent it with a capital S in this situation as well. Or let us start with the variable E, right? So the start variable will be E here. So what are the rules? The set of rules, let us see. So we can define the rules for this language as we can have either simply we can either simply have let us say E plus E and E star E and the brackets, and finally it can be A and B, or let's have epsilon. No, we cannot have epsilon, so let's not have epsilon. Okay, so this is a grammar for this. Alright, so let's see if let's take a small string A plus B star A. So why do we call this grammar as context free grammar is because suppose because we can substitute E with any of this without any context, right? We can substitute any of this in any of the contexts. So here, as we require this expression to be derived, and we know that this is a valid expression already, right? Let's see if this grammar can help us derive this expression. So we can take this as E star E for now, and let us substitute this E with parenthesis, which is this, and we can substitute this E with again E plus E, and let's have E as A over here, and A plus B, and finally A plus B, and let us substitute this E with A, right? So we can derive this string with this grammar. So the derivation of this expression from this grammar that you saw here is called leftmost derivation, LMD. And what is RMD? Which is rightmost derivation. Here we substituted the leftmost variables first, right? This E first, and again this E, then this E, then this, and finally the E which is towards the right. Similarly, in rightmost derivation, we first substitute the variables that are in the right hand side of the expression. So we have to take this, so E star E. Now let us substitute this E first, as it is rightmost derivation. So here we have to substitute this with A, so this with parenthesis, E with parenthesis, and again this E with E plus E, and A, E, oh sorry, yeah, we must substitute the rightmost variable first, so this E first, so B star A, and E will be finally A plus B star A. So as you can see here, we have derived the expression with rightmost derivation. The next concept is the concept of parse tree, and here is where we come to the concept of ambiguity in context free grammar. So, let us take the rule set down so that we can also this expression, so that we can draw parse tree. So let us first take E as starting node. So as you can see, tree should have a root node, right? So here the root node is the starting variable, that is E here. So we shall have the child nodes which constitute this. So E is 1, star is 1, and another A is 1. So E, let us have the child node of this E, which is this for this expression. So here we are deriving the expression with the help of tree. So right, we should have all the characters separately in different nodes. And this E will be substituted with E plus E, and finally this will be substituted with A. So far everything is good, right? But now let us take a different string. A plus B star A, the one with no parenthesis, right? So let us have the root node E. Here we can either start with star or plus. So out here let us start with plus, right? E plus and E. This E will be A, this E will be E star E, and finally we can substitute with A, sorry, this is B and this is A. So we have derived A plus B star A, A plus B star A. Can we have a different tree that derives the same expression with same grammar? Let's see. This time let us take E star E first. So e, and this is e plus e, right? E plus e, and this e will be a, and finally this is a and this is b. So we have derived a plus b star a. As you can see here, there are two ways to derive this expression from the same grammar, but this causes ambiguity for computers to compute uh, and parse the string and validate the string. So this should not be the case, and this creates the ambiguity in the grammar. And now let us see how can we uh, overcome this ambiguity. So we can overcome this ambiguity by prioritizing the symbols and having the priority between the symbols that cause ambiguity, right? Here we can see that a and b are not causing any ambiguity, right? It's always plus or star which causes the branching that causes ambiguity here. So we shall prioritize star this time, and we'll have plus with less priority. So here we shall divide this expression into, we have expression, we shall divide this expression into term and a factor and finally the symbol, right? So we have the expression. So since we are going to prioritize plus, we shall have, sorry, since we are going to prioritize the asterisk, the star, we shall have plus in the expression first, so that the star comes at the lower part of the tree, right? So this is the tree that we are seeing as idle, and this is not the tree, this is the tree which we are avoiding, right? So let us take e and plus t or simply t, because expressions can have simply plus, or simply have asterisk only and not have plus, right? So let us have this rule. So these are the variables, and then the term will have asterisk, right? Asterisk, f, and will have the parenthesis at the end, right? So we'll have parenthesis at the end, because parenthesis is the most prioritized symbol over here. So, and we'll have I as either A or B. So now let us take the same expression, a plus b star c, and draw the tree. We have e as the root node, and as you can see, we have only one option. Since we have plus in the expression, we shall have to take e plus t, right? And we'll take e as t here. So since the left side of plus has no other operators, let's consider it as t. And again here, since there is no asterisk, let us simply substitute it with f, and again it does not have any parenthesis, so we'll have to substitute it with I, and finally we can substitute it with a. And this term t, we can have t star f, right? And this t will substitute it with f, and f with I, and I finally with b. Oh sorry, c is not in the alphabets, right? So this is a, and again f we shall substitute it with I with finally a. So we have the expression over here, a plus b star a. So we have only one tree with this grammar, so this is ambiguity free. So this is a context free grammar, and the ambiguity in that grammar. Now finally let us cover the pushdown automata. The pushdown automata is used for non-regular expression. The regular expression as well can be used, can be expressed in the form of pushdown automata, but it's not required. So now let us take one of the non-regular expression that we derived previously, that we proved that it is not regular. So we have 0 to the power n and 1 to the power n. So let's take this language, pushdown automata. So let's take language with 0 to the power n, 1 to the power n, where n should be greater than or equal to 1. So here what we are going to do is, so pushdown automata is represented as a set of these components. The first one will be the states in the pushdown automata, and we have the set of alphabets sigma, and the stack we can see that why we have push down, right? We use push operation in stacks, so we are going to use stack to track the number of zeros, and again repeat once the same number of times, right? So we are going to use a stack, and we'll have a function, delta function, the transition function, and a starting state, the top of the stack or the starting, sorry, not top of the stack, the starting state of the stack, the first the top element of the stack initially, and we'll have final state, right? So how are we going to represent this language in this form? So we'll have one state as initial state q naught, and we'll also have a stack z naught with the initial state of the stack here, which contains only the element z naught. And let's start with q naught. When q naught gets 0, how should it behave? Suppose it gets q naught, suppose the q naught gets 0 and the top of the stack is z naught. It should be in the same state q naught, but also keep the track of the number of zeros in the string already, right? So it should push a element that indicates that. So let's push a in the stack whenever it the automata gets 0. And again, if gets 0 and the top is a, then we should push another a to the stack like this. And pushdown automata is like NF8. We need not account to every transition for every state, right? We'll have to define only the required transitions. So this is one. And finally, when it encounters 1, it should go to the next state q2, and it is obvious that it should have the top element of the stack as a. It cannot be z naught, obviously, and that top element should be removed. So we represent that with the epsilon. And if you can observe here, the top element initially will be z naught and it is concatenated with a, which means a is added to z naught here and it is written as a z naught, and here also it's only a, and then we have a b, right? Sorry, a, right? So, and finally we'll have a self loop here so that we can empty the stack. So when q2 gets 0, and the top state is a, sorry, when q2 gets 1, that is what we require, right? We only require once after this, right? So, and the top state is element is a in the stack, then we remove that a and accept the 1, right? So we remove the a, and so on. If we again get the 1, we push all the a's out, and finally we have z naught here. So we shall remove this z naught so that the stack is empty, and that indicates that we are in the final state, right? So epsilon and z naught, and we remove the z naught, right? So if any string reaches this stage, we accept that string, right? For example, let's take 0 0 0 1 1 1. So we have z naught initially. So q naught gets 0 and z naught is in the top, so we push a and we accept the 0. So next again it's a 0, so we push again a, and again it's a 0, we push another a, and now we get 1. So we are going to do this transition. So we are going to remove a, pop a and accept it, and again 1, so accept it, and again 1 and push, pop the a and accept the 1. So we can derive this string from this automata. Now let us take an invalid string to check if this automata does not validate that string, right? We'll have 3 zeros and 4 ones, right? So we'll have to push a when q naught gets 0, and again a, and again a, right? Because 3 zeros. Now we do this transition when it gets 1, so we pop a, again this transition, pop a and pop a. But now when q2 gets 1, the top of the element is, the top of the stack is z0, so we don't have any transition to handle this situation, right? So this is the end, and we do not accept this string. So this is pushdown automata, and here we consider a string as accepted when the stack is empty, right? We can also have a state, final state, which makes which indicates that it is accepted. So here we can either have z0 popped or not, right? We can either have z0 popped, or we can simply leave z0, because we have final state that indicates that the string is accepted. So this is pushdown automata. So here we can define delta functions. So the delta function, when it is the state is q0 and it gets 0 as input, and the top is z0, gives the state to which it goes and the top of the stack after the input, like this, right? So q0 when 0 and a, it can be written as a delta q0 when it gets 1 and top is a, we get q2 and epsilon, right? And when we have q2 and 1 as input and top is a, we go to q2 again, and finally when q2 doesn't have any input and the top is z0, we go to the final state q3. Here it either can be z0 or epsilon, right? So this is pushdown automata. Thank you for watching this video, and let us meet in the next video. Thank you.